All right, what we looked at previously on graphing was the basic functions. Now we're going to extend that to higher level functions. And the basic ones, we only looked at x to the first, x to the second, and x cubed, or the square root of x, cube root of x, the absolute value of x, are a piecewise defined. We're going to extend that to higher degrees now. So let's start with the odd degree functions. So we'll look at what happens if we're plotting ax to the n. Let's look at x cubed first, and then we'll look at how it looks compared to x to the fifth. They're symmetric with respect to the origin. Remember, if you plug in -1 for x, or plug in minus x, you'll get minus the answer out. So they are symmetric with respect to the origin. There's x cubed. That's an xy table for that. There's an xy table for x to the fifth. If you plot them, the blue line is x cubed. Goes through the origin, goes up on the right, down on the left. The red line is x to the fifth. Goes through the origin, goes up on the right, down on the left. So very similar behavior. But the higher exponent results in a number that goes up much more quickly. So it's closer to the y-axis if you're less than -1 or you're greater than +1. If you're between plus and -1, you're squeezed toward the x-axis. So what happened is that section between -1 and +1 kind of flattened out more. If we did x to the seventh, we'd see a similar thing, and it would come up inside the red line, but it would be flatter in between. If you kept increasing that exponent higher and higher and higher, what you would be tending toward is a square function. You never get there, of course, but it would tend closer and closer to being a square. If you have the even exponents, we'll look x squared, you know, as a parabola. If you look at x to the fourth and x to the sixth, they're symmetric with respect to the y-axis. If you do the parabola, it would be outside the blue line. The vertex is at the origin for both of these. The red line is closer to the y-axis. The red line is flatter on the bottom. And if you kept increasing the exponent above 6, 8, 10, 12, way on up, it eventually would become a square shape. But it, obviously can never get there. So they have these types of functions have similar behaviors. The odd degree functions are going up on the right-hand side and down on the left-hand side, and they go through the origin. As you increase the size of the exponent, it gets flatter in between plus and -1. For the even degree, both ends go the same way. The basic ones, they both go up. As the increases, you'll get closer and closer to the y-axis. It'll get flatter on the bottom. And remember the transformations we looked at previously? If we have a constant greater than 1 multiplying the function, we're stretching the graph away from the x-axis. It's anchored there, but we're stretching it away. If a is between 0 and 1, then we're squeezing it down toward the x-axis. Remember that if we have a negative outside the function, we reflect up and down. If we have a negative inside the function, we reflect left and right. If we add something to a function outside the function, it shifts it up. If we subtract, it shifts it down. If we subtract inside the function, we shift to the right. If we add inside the function, we shift to the left. If we put all those together, this would be, depending on what this is, it'll either be an S shape or a U shape. If this is odd, it'll be an S shape. If it's even, it's a U shape. This will either reflect it up or down. This is going to move it to the right that many units. This will move it up that many units. So we can start with a basic shape and do all those things to it. So we can actually start from an x cubed, and we could, get an idea what a 10 times x minus 3 to the 15th power plus 5 it looks like by doing a combination of those transformations. For instance, x to the 5th minus 2. Our basic shape is the x to the 5th, which we saw that's an odd function. It's going to have that S shape, but it's going to be flatter near the origin. The minus 2 outside the function is going to move it down by 2 units. So it's going to look like that. That's x minus 5, x to the 5th minus 2. X plus 1 to the 6th, even degree, both ends the same way. Plus 1 inside moves it to the left by 1 unit. So it's still going to be anchored on the x-axis, but it's going to be 1 unit to the left. And it's going to be flatter on the bottom. There's a noticeable flatness down here because we're at the 6th power. Whereas a parabola is all curved, this is looking much flatter. We have both moving right and left, movement up and down, multiplication, and the basic shape. The cubic is up on the right, down on the left. We have a minus. That's going to flip it over, make it up on the left, down on the right. The minus 1 inside here is going to move it to the right. The plus 3 is going to move it up. So down on the right, up on the left. We're stretching it away, so it's going to be elongated vertically. We have moved it 1 unit to the right, and we've moved it 3 units up. But otherwise, it's that basic S shape. With these kind of modifications, we can get there. All right, moving on to newer material we haven't talked about yet. If you're dealing with a polynomial function, unless otherwise restricted by the problem or other statements, the domain of this polynomial function will always be minus infinity to plus infinity, all the real numbers. They're smooth, continuous. There are no gaps. You can draw them without lifting your pencil unless you have some other modification causing that to change. The range will depend on what kind of function it is. If it's an odd function like a cubic, or actually a first power, x to the first, x cubed, x to the 5th, those are the ones that one end's up and one end's down. The range will also be minus infinity to plus infinity. So we'll look at that in the next slide, but let me finish this here. Because one end's going up and one end's going down on an odd function, somewhere it crosses the x-axis. You can't get from plus infinity to minus infinity without crossing the x-axis. So at some point, the function value will equal 0. That's when you're on the x-axis. That value is the x-intercept, and that's a solution to the equation that the polynomial represents. So here are odd degree functions. There is a third degree, and because of where it's located, it crosses the x-axis 3 times. Every one of those places it crosses is a real zero. So those zeros we were looking at previously, that's those points on the axis, those numbers we came up with. If that had been shifted up or down, we may have only crossed one time. In that case, thinking back to what we talked about yesterday, that would be where there was one real zero and two imaginary zeros. Because remember, your imaginary ones must occur in pairs. Here's one that is shifted up. Still third degree, it's still a cubic, but because it's moved up, it only crosses the x-axis one time. This would have one real solution and two imaginary ones. If it's shifted down, same sort of thing, but there will always be at least one real. It has to be because it's an odd degree. Here is a fifth degree, but there are only three real ones. Two of them are imaginary. Again, it has to occur in pairs. So there will always be an odd number of real zeros when you have an odd degree function. Always an odd number of real zeros. If you have a polynomial function that's even degree, the squares, the fourth, the sixth, because both ends go the same direction, it might cross the x-axis, it might not cross the x-axis. If you're opening upward and the vertex is above the x-axis, then it never crosses the x-axis. If it's below, it'll cross twice. Similar sort of comments for if it opens downward. The range will either go from negative infinity up to a number, so it's either going to be like this, or it will start at a number and go to positive infinity. The domain is still minus infinity to infinity, but the range depends on the function. It will always be one of these two types. Typical functions. Here is a fourth degree polynomial function. Both ends go the same direction. In this case, it only crosses the x-axis twice. Again, the imaginary numbers must occur in pairs. So every even degree function will have either 0 or an even degree of real zeros. It might not have any. You might have 4 imaginary. Because if we shifted that all the way up above the axis, it would never cross and you'd have no real zeros. Here is a sixth degree with 4 real zeros. In this one, this minimum point here is where the range begins. So the domain is minus infinity to infinity. The range begins here and goes up, so it's k to infinity. Over on this one that's opening down, both ends going down, then the range is going to be from minus infinity up to this maximum value of k. So even degree have a beginning or an ending point in the range. Odd or infinity, both directions. And referring back to multiplicity, when we're talking about the graphs of these functions, it's possible that we may have a repeated root, which means a multiplicity. So if we know what the multiplicity of that 0 is, in other words, does it occur more than once? Well, because it's the same number, that puts you at the same point on the x-axis. So if it's a real 0 that occurs more than once, that will put you on the x-axis twice at that same point, or multiple times at that same point. How does that affect the shape of the graph? That can help you when you're trying to draw the graph. If you have a multiplicity 1, which is what most zeros are, the zero only occurs once, then what happens is the line comes up, crosses, and keeps going. Or it's coming down and crosses and keeps going. There's no change in the shape of the line as it crosses. It just goes across. That's multiplicity 1 type zeros. No effect because it's crossing the axis. If you have a zero of even multiplicity, then it doesn't actually cross the axis. At that point, at that zero, it's tangent to the axis. It's either tangent below or tangent above. So even zeros of multiplicity higher than 1 are tangent. Odd multiplicity, 2 characteristics. It's going to cross, definitely go across, but at the point where it touches the axis, it becomes tangent to it, and then it goes back up. So if you're coming up, this comes up, flattens out, and then it starts up again. If you're going down, it flattens out at the point it crosses, and then starts back down again. So an odd multiplicity crosses the x-axis with a point of tangency, but it does go across. Even multiplicity does not cross. Odd multiplicity does. And something we saw on earlier slides, sometimes a graph will be moving in one direction and then it'll turn around and go the other. The point where it stops going down and starts going up is called a turning point. And one of the facts about polynomial functions is that it will have fewer turning points than the degree of the polynomial. If you have a cubic polynomial, you can't have 3 turning points or 4 or 5. The most you can have is 2. You may only have 1. So a polynomial of degree n has at most n minus 1. Doesn't mean it has all of those. It may have fewer. If you have multiple real zeros, then you have to turn around in between. So when you're either going to touch the axis or cross it to get one real zero. If you have another one, you're going to have to turn around and come back to the axis. So there has to be at least one turning point between successive real zeros. There could be multiple turning points between. The end behavior of a polynomial graph behaves the same way that the highest degree term behaves. That's called the dominating term. So if you look at the term that has the largest exponent and think about the basic function shape for that degree, that's what the ends of that function will look like. So if you have a polynomial function like this, if we look at this highest degree term right here, the two ends of the function will behave as if these other terms weren't even there. That term, if x is large enough, that term dominates all the rest. It's like these weren't even here, and so it behaves like this. So the ends behave that way. We can look at this then, and if that's an odd, we know one end's up, one end's down. If it's even, both ends the same way. No matter what else is tacked on, that's what the ends do. So f of x equals this function. the graph of that function, if you get far enough away from 0, then the ends are going to behave as if that's the only term in that function. Cubic, with a positive coefficient, the right end's up, the left end's down. So that would be perhaps what that previous one looked like. So it's wiggling in the middle, going up and down, changing direction, all that, but eventually that right end goes up, the left end goes down as x gets large enough. You can state that x goes to infinity as y goes to infinity, or as x goes to infinity, y goes to infinity. Just some of the verbiage on how you describe that situation. Frequently you'll hear approaches or goes or whatever to infinity. If it looks like that, as x approaches infinity, y approaches negative infinity, and so forth. All right, so kind of reiterating, if you have a polynomial function of degree n, and if that dominating term is odd degree, so if your largest exponent in your function is an odd degree exponent, then if you have a positive coefficient in front of that, then the right end of this function is going to go up and the left end of this function is going to go down. Just like, so we're extending this idea about parabolas. Remember parabolas, if A was positive, it opened up, if negative, it opened down. Now we're extending this to other things. We're doing odd degree now. And when A is positive, the right end's up, left is down. It doesn't matter what n is as long as it's odd. That will be true. So any odd degree function, no matter what it's doing here in the middle, if that coefficient in front of that highest degree term is positive, it's going to look like that. If that number is negative, it's going to flip over. The left end will be up and the right end down. It'll look like that. This is called end behavior. How do the ends behave as it goes to plus and minus infinity? Odd degree, they all go in opposite directions with positive coefficient, meaning up on the right. What if it's an even degree function? 2, 4, 6, 8, etc. Parabola, if that's positive, it opens up. Negative, it opens down. Same thing's true no matter what the even function is. If that A is positive, it opens upward. If it's negative, it opens down. Those two ends go the same direction. Up when positive, down when negative. So very simple, straightforward concept. If you remember how a parabola and a cubic function behave, then you can remember all the others. You just have to remember those two because all the rest of them behave the same way. Okay, so what that does is one of the first steps in being able to match an equation and a graph. For instance, here is an equation. Here's a function. Without doing any calculations, we can actually determine which one of these graphs is the proper graph for that function. And what we're going to do is we're going to use, this case, all we need to use is end behavior. The way you do that is you look at that highest degree term, fourth degree. 4 is an even number. Even degree functions, both ends have to go the same way. So we can immediately eliminate this one and this one. No, those can't be it. Secondly, if the number in front of here is positive, both ends have to go up. If it's negative, both ends have to go down. That's a positive number, so we can eliminate this one. That has to be the graph of that function. So there's the graph. All right, so using similar approach, which one is the graph of this one? It's x to the 6th, which means the same direction. It's negative, which means down. So it's A. The cubic here. Cubic means different directions. Positive means right up. Negative would mean right down. So it is B. And we're not doing any calculation here. All we're doing is looking at numbers and signs. Still going to be different directions. It's going to be left up this time, though. This is one of the steps. Now, in general, identifying them, you're going to have to use more than one thing. You would have to use not only the end behavior, but you can use where does it cross the y-axis, the y-intercept. That's an easy one to use also. Does not require any calculation when you have the function written like this. Polynomial function should be written this way. And so in this form, how do you find the y-intercept? What's the value of the y-intercept of this function? -4. All you've got to do is look at this number right here. That's the y-intercept. So you don't have to do any calculation, and you can find that. You can actually, well, you can't get it from here. I think they all cross at -4. But if you combine end behavior and y-intercept, you also might have to combine x-intercepts. In other words, you'd have to find some zeros for that function, which would require calculation. Okay, so the other thing would be the turning points. Remember I said there were only at most n-1 turning points for an nth degree polynomial? That could be a final decision maker. You look at the end behavior, you look at the direction it opens, you look at the x-intercepts, you look at the y-intercepts. You might finally have to choose based on how many times does it switch directions. Because if you have a if you have a cubic function that you're trying to get a graph for, if you've got 4 turning points, or even 3 turning points, well, it'd have to be 4. If you have 4 turning points, it cannot be a cubic. So that could be another deciding factor. All right, if you're trying to graph, if you want a reasonable representation of this graph, it needs to have the following characteristics, needs to have the following things in it. It needs to have where it crosses the x-axis. Those zeros, those are very important things about the graph. The y-intercept, that's also useful. If you're going to do this and you're plotting it, you need to know what happens in between the points where it crosses the x-axis. Is it above or is it below? You need to know how the ends behave. That's going to, you can tell that from the end behavior. So let's look at an example where we're going to actually sketch a graph using those types of things. Find the zeros. That'll give you the x-intercepts. So that gives you some points on the graph. Starts anchoring that down. Find the y-intercept. Plot that. That's also an anchor point. Then in between the x-intercepts, pick points. You pick one point about in the middle between the x-intercepts. That will tell you is the graph above or below the axis at that point. And halfway in between probably is a reasonable estimate of where that turning point is going to occur. Because if it crosses the x-axis twice, somewhere in between it has to turn. And so halfway in between is a reasonable place to guess where that turning point might occur. So that could be, sort of giving you the turning point. It doesn't give it to you actually, but it could be reasonably close. You know that if you get far enough away, the graph has to do a certain thing. So if you're outside all of your zeros, then you can keep it going the same way. Because your largest zero, that's the last time it's going to cross the x-axis in that direction, so you can keep going the way the line's going at that point. So if it crosses going from plus to minus, and that's the largest zero, then keep going. If it crosses going positive, then keep going. Number line type of larger. So whichever one's further right, whatever it's doing when it crosses that, keep going. So here's an example. Cubic function. Have no idea what it looks like. But if we start graphing, if we want to find the zeros, the possible rational zeros are those. We can show that plus 1's a 0. So that means x equals, 1 on the axis is a 0. That reduces it. Now we have a quadratic. We can solve the quadratic. And we get two other zeros, minus 3/2 and minus 2. So there are our three real zeros. Those are points on the x-axis. Look at the constant. Our y-intercept is minus 6. There's a fourth point. So we have 4 points on our graph. They look like this. These are my zeros. This is my y-intercept. Now what I need to do is I need to pick a point between those two zeros. I already have a point between these two. I don't need another one. And I need to pick points outside here and here to estimate how quickly those ends rise. Because I know whatever direction it's going when it crosses the axis here is going to keep going the same way. It's not going to turn around and come back. Otherwise, I'd have a 0 out there. Same thing on this side. So I need to pick points in between. And so I'm going to pick a point halfway between those two. And that should give me a somewhat reasonable estimate of where that turning point is. This one is fairly close to being in the middle between that one and that one. So that's not a bad estimate of where that turning point is. It's a cubic. I can only have 2 at most. That's 2 turning points. My end directions have to keep going the same way. So I picked in to the left, I picked that point, and it's below, and so it's going to keep going down. In that little tiny interval, I picked that point, and that's going to be a good estimate of the turning point between them. That one I already had. That was my y-intercept. And then I picked one out the other side. That's positive, so it's going to keep going up. Plot those. Here's the point I picked in between. I think I picked a point -3, which would be off the graph here. and then I picked one over here too, would be off the graph as well. That just verified what was happening there. Then, you know, draw a smooth curve between those. We know we're not going to have any sudden changes. It's going to be a nice, smooth, changing curve as it goes through the points. So you don't need to worry about any sharp corners or anything. So just draw a smooth curve in connecting the dots. Don't do it with straight lines because they're curves. And so that's a reasonable approximation to the graph. This one I did with Excel, so it's a good approximation. But if you're doing it by hand, then that would be a reasonable. What you're after from a plot of the type where you're doing it by hand is an idea of the behavior. We know we have a maximum somewhere in here. If you're doing a control for a process in a factory, maybe you don't want to be near that. That might cause a problem. Or maybe that's where you do want to be. You want to operate near that maximum. You don't want to get too far out here because that's going to go out of control because you've got uncontrolled behaviors that gets out there. That sort of thing. So a graph in these types of applications is visual feedback to help get an overall understanding of what's happening with that function. It's not intended to be exact. If you want exact, plug numbers in. And notice that every one of our zeros was a zero of multiplicity 1. So every time it crossed the x-axis, it just kept going with no, it didn't flatten out in any way. 2 turning points, there and there, cubic function. That's the most we can have. If we wanted more points, we could if we want to smooth it out. But generally, the number I indicated here should be enough to draw the graph because you're not looking for high precision. Okay, so summarizing some of the stuff, x-intercepts of a graph are the same thing as the zeros of a function, which is the same thing as solutions to the equation 0. So you set that polynomial equal to 0 and solve it, you'll get zeros, you'll also get x-intercepts. Those numbers can then form factors the way we looked at the beginning of class. If you have a 0, x minus that 0 is the factor. All of those really are describing the same information.